Hello, welcome to ISAT431, Advanced Manufacturing Processes and Systems. This is lecture 3, Materials in Additive Manufacturing. So mainly today going to talk about several different materials that are commonly used in 3D printing. Includes metals, alloys, polymer composites, ceramics, concrete, and also lastly going to provide a comparison table to show all the comparisons of these materials in additive manufacturing. All right, let's first look at the cost composition in 3D printing. When we look at the economy of scale, so what happens with economy of scale is that in additive manufacturing, the most of the cost actually comes from the equipment. Because the equipment is very expensive, and the next one will be the material cost. Especially when we are processing metals and some other materials other than polymer. Polymers might be a little bit cheaper, but for metals and other material, it can be very expensive. So in traditional manufacturing, we have this economy of scale when we have the fixed cost of equipment and also facilities, those costs. And if we produce more, means our per unit cost is actually decreasing, right? But for additive manufacturing, because the initial high cost of the equipment as well as the processing it. So processing of the material includes the material itself. So the materials need to be well prepared, and that is the cost. And also there is the processing cost. The labor cost will be also higher than traditional manufacturing because it requires more skills. So that's why we do not really see a very good decreasing curve in additive manufacturing. That's why it makes it a little bit hard to commercialize and have mass production with additive manufacturing processes, at least right now. But there are also some of the benefits of from additive manufacturing of various materials. For example, especially in the metal additive manufacturing, it reduces the tooling cost because in traditional manufacturing we have to make all these tools, right, including fixtures and some other tools that are required in the processing. Also, the freedom design is better than traditional manufacturing because we can create very complex shapes that are so difficult to be made in traditional machining or other processes. For example, casting, then you have to create all these molds in order to make those. And also you can utilize some of the very innovative ways of design. For example, we use topology optimization in order to create structures that is only needed for the function of the part. So this way we can create real lightweight structures, and those structures, those designs has there's a better option to make those prototypes with additive manufacturing instead of traditional machining or casting or some other processes. And also in additive manufacturing, because we are making the whole part, so it also eliminates the part assemblies. And the processes for metal 3D print includes powder bed fusion. We talked about in the last lecture, and usually the accuracy will be around 20 microns. But the problem is all these metal additive manufacturing processes are very slow. It takes many hours to make them. And another process, common process, is direct energy deposition, right? they use electron beams, while powder bed fusion uses lasers. Also, there are a lot of other processes that can also do 3D printing. One is the better binder jetting, so we can take a look at this, or maybe you just watch all these videos when you are going through the slides. Click each one of them, because this lecture we are focusing on the material itself. So you can just watch those videos to see how how metals are actually processed in those processes. And first material I want to talk about in the metals is titanium and its alloys. So titanium has been very popular metal that is used in additive manufacturing, metal 3D printing. It's because of the several applications. One is aerospace, also can be used in medical and automotive industry. So the reason titanium can be used is because it has a really good corrosion resistance and also high strength to weight ratio, and also its biocompatibility, so that can be used in a lot of medical devices as well as implants. And so the common material about titanium will be titanium powder itself, pure titanium, and also we have Ti-64, so which is another alloy that has been used a lot. Titanium alloy has been used a lot in additive manufacturing. And so something to mention is a buy to fly ratio. So the buy to fly ratio in aerospace space refers to the material purchased at the beginning. It's a relation of the material purchased at the beginning versus the weight that is actually used of the finished part in a product. So with additive manufacturing, using a processing titanium means actually we reduce a lot of waste, right? Because it's not a subtractive processing, so we're not subtracting a lot of materials. A significantly decrease this kind of buy to fly ratio. So this is one application, that why reason that metals and titanium can be used in aerospace industry. And another metal is steel. Is also widely used in 3D printing as well. These are some of the common steels you can see: austenitic, stainless steel, maritime steel, and also tool steel. Some of the precipitation hardenable stainless steel as well. And in terms of the steel versus the titanium, mainly titanium has is lighter, and the steel will be a little bit heavier. So it depends on the application, right? So if you need applications that with really high strength and hardness conditions, maybe steel will be a better option. And also steel has been you can use 3D printing to make toolings and also molds with steel as well. And another metal is aluminum. So aluminum is not used a lot in 3D printing, but it also used for some research purposes, because of several disadvantages. The one is aluminum is usually very the cost of aluminum is a lot lower than other metals, right? Lower than steel and also titanium, and so making them through a traditional manufacturing process actually is easier and also cheaper. So that's why it's not well commercialized into industry. And another reason is, aluminum alloys are it's a little bit hard to weld. So if you want to make modification of the shape and also the process, it might create a little bit of barrier. And also, when we created the metal powders, right? We'll have to use lasers to sinter them or melt them. But for aluminum, because it has really high reflectivity, so it makes the laser waves a little bit hard to be absorbed. So that's why another reason that it's hard to make aluminum 3D printing parts. And one advantage of aluminum is that it has really high thermal conductivity and also reduces internal thermal stress, and it allows for faster additive manufacturing processes. Some other metal materials that are also used in 3D printing include nickel, cobalt, chrome, and alloys, and also some other metals like magnesium, copper, and gold. And about cobalt chrome alloys, it's being used a lot in biomedical areas. It's because of the characters of wear resistance, biocompatibility. Also has a high melting points. And it also good strength to high temperatures. So these are that's why cobalt chrome has been used a lot in the biomedical industries. And there are a lot of research going on to explore 3D printing of many other metals. But apparently those processes are still in the research area instead of being commercialized into production. So this is just something to let you know that in the future, maybe after 2 or 3 decades, you'll see those 3D printed commercial parts. And some of the qualities that affect the some of the factors that affect 3D printing, metal 3D printing processes, and also the quality, is that the feedstock. So usually the feedstock is for metal and alloys 3D printing is the powder, right? So in powder metallurgy, remember when we talk about in ISAT430, there are several factors about powder. One is particle size and also particle shape, surface roughness, porosity. Those are the characters. It all same. So the feedstock quality of the powder quality also affects the quality of the metal 3D printing parts. First, particle size. So the particle size really determines the layer thickness. So if the size is big, then the thickness is higher. Higher thickness actually creates more porosity and also decreases the density of parts and it causes some rough surfaces, right? And so a preferred size or commonly used size for metal powders will be 15 to 150 microns, so that it can create a higher density and also lower surface roughness. Another one is the particle shape and the surface and the particle surface roughness itself. So particle shape, there can be different shapes, right? And circularity will be preferred. And high spherical shape particles usually with smooth and dry surfaces usually will yield less internal friction. And if some other particle shape, it will create some more porosity because it's not well condensed. And some of the shape factors, for example, the aspect ratio, elongation, dispersion, roundness, flatness, perimeter to area ratio are also going to affect the the particle shape. And for the porosities, so the porosity inside of the structure are actually stress concentrators. That's the place where a lot of stresses are going to concentrate and have a lot of stresses. And if there are a lot of porosity, then we'll reduce the mechanical properties, for example, the strength, right? And also going to create easily get fatigue. For example, get damages from macro cracks, and those cracks will getting bigger and bigger over time. But for some of the applications, it might prefer porosity. For example, when we are making some of the implants, right, to use metals to build those implants that, for example, to use it as a bone, because the bone has a lot of porosity as well. So there's a fusion process, when we put an implant into the body, and the bone will actually start to grow inside those. And if there are a lot of good porosity of the implant, it can actually have a better fuse between the implant and also the part of the body. So that's one application that you want to have higher porosity, but in most of the other applications, porosity will actually gonna cause a lot of issues in metal 3D printing parts. And also, there are some of the processing parameters affecting the quality of the 3D printing parts, the metal 3D parts. During the process, we know the main factor is the laser. So it really depends on the scanning speed and also laser power, because they will affect the solidification of the part. If the scanning speed is fast, and then think about this: when you have the laser gonna melt the material at one spot, right? Powder at one spot, and it goes away. So after it goes away, it will start to solidify, and then what happens later is that it will actually come back, to the original point, because it's gonna scan several times. And then, what happens is they're going to start to have the edging effect. And those edging effect going to cause some of the quality issues of those. And, of the fusion, and also the sintering. Well, another factor is the laser power. So the combination of the two really determines the solidification process of the powders, and also this is how gonna affect the quality of the metal 3D parts. And for the metal 3D parts itself, as a general part, so the dense metallic additive manufacturing parts present a comparable quality to conventional manufacturing. So the question is, how do you come up with dense metallic additive 3D printing parts? So you can you can improve the density by using better feedstocks, right? And also you can have some of the post-processing processes. For example, condense the part after it's 3D made. And for as to the strengths, 3D printing metal components usually have finer microstructures than conventional made parts, but 3D printing parts have this anisotropic character, because it is always built in one direction. Right? So this also might affect the strength a little bit, because the stress directions and also will be a little bit different. And surface roughness, and so 3D printing parts, metal parts, are also increased some of the surface roughness because of the different layers of the powders, and that will cause this stress concentration at the surface level as well, and also might create the early failure of the part. So that's why usually after those we have to get some of the post processing, for example, grinding or surface treatment, in order to increase the surface finish of the 3D printing parts. Another material that is also used in 3D printing is the polymers and its composites. So common polymers that are used are ABS or PC or PLA. These are some of the names that we hear a lot, and the forms of those materials, it can be filament. We see this a lot in fused deposition modeling, and also there are some reactive monomers, resins, and also powders. So for example, in SLS, right? So it has been we can use the resin to use a laser to sinter those. And so photopolymers actually widely used in 3D printing. It's because because of the process itself, right? The resin can polymerize when it is activated by UV light, and also for polymers, because it has a less strength than the metals, so the thermal mechanical properties is always an issue in polymer 3D printing parts. It's just because of the character itself, property itself, and so for the polymer additive manufacturing, it really has a better accuracy, and also we have thin layers and fine precision with SLA. For PLA, PLA is actually environmental friendly. But for PLA, maintaining optimum resin viscosity is at a low temperature is a little bit hard, so that's why it's gonna create some of the issues in the process. So one way to solve this issue, we can increase the temperature during the process. But if you increase the temperature, you're probably gonna cause some of the thermal property change, of the material. So that's something you will have to balance. Well, another solution is to use some plasticizer, right? And also we can prevent some of the thermal degradation. And some of the plastics for selective laser sintering includes polystyrene, polyamides, and also thermoplastic elastomers. And the processes are being used a lot in polymer and composites processing. It has stereolithography, infused deposition modeling, selective laser sintering, and also inkjet printing, right? These processes we'll talk about in the last lecture. And in terms of the fused deposition modeling, this is the most common process we see a lot in our lives. And for the composites and thermoplastics, usually we use them because they have low melting points, and if it's with higher melting temperature, it requires the nozzle have a higher melting temperature, and that might cause some of the fluid or deposition issues as well. ABS, it has a good mechanical property, but it has kind of an odor that kind of affects the breathing. So that's some of the defect. While PLA is even environmental friendly, but the mechanical properties can be a little bit poor. But in some of the research, it actually shows 3D printing at PLA showed enhanced mechanical properties compared to injection molded PLA. And so the polymers can also be mixed with metals or ceramics. Mixing those to create composite material is to increase the property of the material, and also for the part. And so one is a fiber reinforced materials, the carbon fiber. With polymer feedstock, it can actually increase the strength and stiffness and reduce distortion of the part. And also it can be mixed. Polymers can be mixed with titanium alloys. Usually that's the photopolymers, and we can create some very complex composites as well. And also can be mixed with ceramics like alumina powders, right, to create a polymer matrix. And the properties with those products will show better wear resistance, and also it can create some of the filaments that with nanofillers in it. And for the nanocomposites, some carbon nanotubes can be used to mix with polymers as well, and usually those nanocomposites actually have very good thermal conductivity, have a good fire performance, and also the strength and strength to weight ratio is very good as well. So another material in 3D printing is ceramics. So processing of ceramics usually that's difficult because melting and also sintering in the ceramics usually requires really high energy. But ceramics materials have a lot of advantages. One is it has a wild applications in biomedical area. For example, biomaterials and tissue engineering, right, bones and tissues. So those applications have triggered the creation of this 3D printing of the ceramics. And a drawback with 3D printing of ceramics is that it has a layer by layer appearance. Also, the selection of material is very limited. We remember at ISAT430 we have the matrix of creating the ceramics, and not all the metals can be actually to create ceramics. And also the post processing is required because of the we have to center the internal structures of the part, and it's a time consuming and costly process. So the common practice is we create the shape with 3D printing, and then we gonna use the sintering or fairing to bound the materials. And common processes are inkjet. So inkjet is it's the main method of creating ceramic parts, but there's a kind of a breaking and also thinning issue related to the printed the filament. And also the viscoelastic behavior of the inks will also gonna affect the the printing quality. So ceramics can also be used in the selective laser sintering. But because ceramics have this kind of a thermal shock behavior, when we are using high heat, and then cools down, or start have this solidification, and it can lead to some crack formation in some of the parts. So that's one thing we have to be careful when during processing of the ceramics in SLS. So some of the research has been going on to create a process called selective laser gelatin. And so this process is to use a binder, right? To binder to create create a gel shape, right? Create a gel of the material, and then use the laser to to create that kind of shape of the part. So the shape of the part will be called the green body. Then the green body will be centered, at higher temperature, and then to create the final parts. And usually is used in ceramic glass or ceramic polymer composites. You can see some examples from the pictures what they made. And some other processes, for ceramics will be the paste extrusion. So the paste extrusion is more like fused deposition modeling, right? And you just have the ceramic paste, right? And then you extrude it, through the nozzle. But usually after that, there is a post-curing process required, because the extrusion itself is just to create the shape. Bonding of the particles of the structures also requires the sintering process. So that's why post-curing can be important. It changes the face of internal structure of the material, and also it gets all the water out. We can use either UV light or heat to for the curing process. And some of the factors that affect the quality of in the paste extrusion will be the rheology factors. For example, if the high viscosity slurry actually is not very good for deposition, and also the particle size distribution, because it's combined with it's particle combined with a liquid, so that's to make the paste. So the packing of the particles also a factor for the paste. And some other factor will be the temperature, the air entrapment, the drying, debinding procedure, and solidification. And also interlayer adhesion. Also, these are the factors affecting the paste extrusion. And the process for making another process for making ceramics is 3D printing ceramic parts is direct ceramic stereolithography. So it is similar to the metal stereolithography process, and also same with the polymers. So when we have the resin, and then gonna use the laser to center the resin to create the green body. It's same with ceramics, and usually we use smaller ceramic particles with better light scattering properties, or it can actually shows a better quality, and also it can produce a very smooth surface finish. Another material for 3D printing is concrete. So concrete, as we seen from from the video in the last lecture, mainly the process of the contour crafting. So similar to fuse deposition modeling, and so the property affecting the or the factors affecting the quality of the process will be similar to the fuse deposition modeling, which is the extrude if the paste, right, if the concrete paste can go through the nozzle freely. And also there's rheological properties issues, for the mixture, the pumping and printing. If the viscosity is really high, it will cause some of the deposition, right? So also when we are printing concrete materials, we're gonna create different layers. So and have a high early strength of the concrete, it can actually support subsequent layers on top of it. And so the material for those concrete materials is actually generally it's the fiber reinforced mortar. It includes of the Portland cement, fly ash, silica fume, and sand. You can also control the fiber orientation in a printed structure. Some of the challenges will be interlayer adhesion. So smaller size can result into higher strength because of the better interlayer bonding. So it really depends on what is the thickness of the print. Something is we're not sure is lifetime duration. Compared to traditional, structures, either in the construction industry, versus the 3D printed structure. What is the lifetime duration or durability? This is still under study. So the more need to be understood for this process. And this is a comparison table of all these materials that are commonly used in 3D printing. So metal, polymers, ceramics, concrete. You can see the different applications, the benefits, and also the challenges of comparison table. So look into this table and have comparison, and I think in the future, if you have a chance to do more 3D printing with materials other than polymer, it can provide you with a guide of choosing what kind of metal it should be used, and also during the process what factors need to be considered in order to create a better 3D print parts. All right, so that's all for today's lecture.